Welcome back to Physics 246 Online. I'm going to give a brief overview of the material from Chapter 6 in Bevington Robinson, which has to do with the method of maximum likelihood applied to a linear function, otherwise known as the method of least squares. The question we're trying to answer is, what's the appropriate condition to be used to determine whether the sample population is representative of the parent population we think it came from? So, for example, here's a sample population. Perhaps we measure the height that a plant grows to in a certain time when that plant is kept a particular distance away from a light source. And so we measure plant height versus distance from light source and suspect that there may be a linear relationship between these data. In other words, that these data that we measured, complete with the error bars that represent the uncertainties in the measurement of the plant height, they come from some hypothetical parent population that has a linear form. So we first assume just that these data come from some parent population that has a linear relationship where there's values of two parameters, a0 the intercept and b0 the slope, that relate y to x, in this case the plant height to the distance from the light source. The problem is that based on our sample, we'll never know the exact value of a0 and b0. We have a limited number of data points, and we also have uncertainties to deal with. So a solution to that problem is attempt to use the data to estimate through some kind of rational procedure what our best estimate is of the parameters of the parent population. In other words, the a0 and b0. Second assumption is that we can use our sample population, and here's the method, to determine the most probable population from which those data came, the y equals a plus bx. This population, once we determine the values a and b that make it most probable that the data came from this linear equation, they will approximate what the values are that characterize the parent population. And in the limit where we make lots and lots of measurements, where a number of data points becomes very large, the a and the b that we determine from our sample population will approach the a0 and the b0 of the parent population. These are our assumptions, and now we're going to show how to use them to do this calculation based on the maximum likelihood method, which we already used back in Chapter 4 to justify calculating the average as the best estimate for a value of a measured quantity based on repeated measurements. So, in the absence of any random measurement fluctuations, of course, all the data points would be in perfect agreement with the parent population according to this equation here. So to simulate what we observe, we need some kind of a function, a mathematical function, that represents these random measurement fluctuations. And of course, that function is going to be a Gaussian function. So how do we use that to calculate the probability that our data points came from the parent population, or the population that has the values a plus b that is going to be our estimate of the parent population? So if we make a measurement of, given a particular value x, we measure the value y along with its inherent uncertainty, the Gaussian function tells us that the probability of getting exactly that data set would be the following, right? Where the y of x sub I is our assumed parent population. The y sub I is the individual data point that we measure at a value x sub I. The y of x sub I is the value that we would get based on this expected functional form. So the quantities that match up here, the x sub I values, the y sub I value, and the sigma sub I values should be fairly clear. So at each data point, we've measured y with a particular uncertainty. So y of x sub I is the value of y at that particular data point x0 that's expected from the parent population. So let's think for just a second about what this term inside the exponential function represents. All right, so the y minus the y sub I of the data point minus the expected y from the parent population function is a measure of how much deviation there is between those two quantities. The denominator is our uncertainty in our measurement. And so one might expect the numerator and the denominator to be quite similar if the data actually do come from a particular kind of parent population. So the probability, once we know what the probability is of getting any one measured data point, then now the total probability of getting our entire set of measured values, where I runs from 1 to n, would simply be the product of all those individual probability functions. And we did something like this again, remember, back in chapter 4. So when you do that product, and the pi represents the product of all those terms, you get something that looks like this, where you've got some constants out in front, and you've got this somewhat familiar now exponential factor, where since it's the product of a bunch of exponentials, we can write it as the exponential of the minus 1/2 quantity times the sum of all those terms that appear in the individual exponential functions. So we're going to call this quantity, since we've just talked recently about the chi-square value, we're going to call this quantity that's inside the summation the chi-square value for that particular data point. And that makes sense because look at this quantity. It represents a difference between the measured value and the expected value squared over the uncertainty squared. And so that's very, very similar to the way we defined our chi-square value when we were talking about a particular distribution function. So this is chi sub I for any individual data point. Then when we want to do the sum over all the data points, we'll call this the total chi-square value. And that arrow should point just to this sum itself. So our job, and here's the method that we're going to use, the maximum likelihood method, our job is to figure out the parameters of this function y of x sub I, which we assume for this purpose is a linear expression. We want to find the parameters that maximize this probability, that maximize the probability that we got this data set from a particular parent population. So in order to maximize the probability, since the exponential term has a negative in front of it, we basically want to minimize this exponent. So we're minimizing the chi-square value. The chi-square value is the sum of the individual squares of these terms, and so that's why this method is often called the least squares method. What I just said, that just summarizes it right there. So when we minimize a function, what do we want to do? We want to take some kind of a derivative. Only here there are two parameters in our assumed function that describe our data. There's a slope and there's an intercept. So in order to find the values of the slope and the intercept that minimize this function, we need to take the derivative of chi-square with respect to a and with respect to b and set each of those two quantities equal to 0. Back in chapter 4, we only did this with respect to one parameter, and that was the mean. When we do it with two parameters, voila, we take the derivative of chi-square with respect to a, set that equal to 0, and the same thing for parameter b. And remember, parameters a and b are in that function that we assume our data came from. These two expressions, when we take the relevant derivatives and set them equal to 0, we get the equations that are listed in the textbook. So just to illustrate, here's the derivative, and we write these as partial derivative now because chi is a function both of a and of b. So we take the derivative of this chi squared. Now that we put explicitly into the expression our expression for y of x sub I, which is a plus bx sub I. So we put this in here. Taking that derivative with respect to a, right, the 2 comes down in front along with a minus sign because the derivative of the argument here with respect to A is going to pull out a minus sign, and that's all that we have. We do the same thing with respect to B, and we get something that looks quite similar, only the B value here had x sub I in it as a term that multiplied it, and so this also pulls an x sub I outside when we take the derivative. So these are equations 6, 10 in the textbook. And if you look carefully at these results, we've got two simultaneous linear equations. Two equations with two unknowns, A and B. So we need to satisfy these two equations at the same time. What does that do? We have this expression that we obtained on the previous slide. Then, if we just remember that the sum of this expression could be written as individual summations, and then we take the A term and the B term and the sums involving those and move those over to the right-hand side of the equation, we get this result here. There's a sum of y sub I over sigma I squared is A times the sum of 1 over sigma I squared plus B times the sum of xi over sigma I squared. So we're going to need these summations using our measured data points in order to solve these equations. We get, again, something very similar for the equation where we're differentiating with respect to B. The details look just a little bit different, but you basically can see in these two terms here, you've got something on the left-hand side that involves the measured value y sub I, and then two terms on the right-hand side, each of which is multiplied by A. So there's a way of expressing these in matrix form. We can write these down as in matrix form by having a column vector on the left and then a 2 by 2 matrix on the right-hand side. And when we do that, you might remember from your linear algebra that you've taken, or if you haven't taken it yet, that's okay, you can express the solutions for A and B using the determinant of that 2 by 2 matrix, which appears on the right-hand side of this equation. So what we've got here is 1 over delta. We'll define what delta is in just a minute. The elements of this 2 by 2 matrix here are the summations over all the data points of these quantities. And the determinant means you take the product of the diagonal here minus the product of this diagonal here, which is why the value turns out to be what's given on the right-hand side. For the B parameter, again, something very similar occurs. And in both these expressions, the delta is this determinant here. So when we solve for A and we solve for B, there's going to be all kinds of summations involved, but some of them are repeated. For example, you can see here that we get this sum 1 over sigma I squared that appears in the B term. It appears again in the delta term. And so calculating these things isn't really too difficult, and you'll be doing this for practice, for homework. So these are equations 6, 12, and what they give us are the best values of A and B that we can extract from our data set. And remember, what we've done is we've found the values of A and B that make it most probable that our measurements came from the parent distribution. So we've determined A and B, and that's only half the job. Now we also need uncertainties in the A and B values, because if A and B are some physically meaningful quantities, we need to know what our ultimate uncertainties in those is. So we're going to go back to the error propagation equations from chapter 3. There's going to be one like this, sigma A, and you have to think a little bit about what does A depend on, right? A depends on the values of y that we measured for our relevant data points, and we have n of those. So there's going to be a long, long equation here where you've got a term in this equation for each of the data points from 1 to n. Same thing holds true for sigma b squared. We now have our expression for A and our expression for B from the previous slides, and we can take the derivatives of those expressions with respect to each of the individual y values that we measured. So again, this is a lot of terms potentially in this sum. We'll have one term for each of the data points that we measured. So we can calculate those derivatives here. I won't work through the steps of it other than to show what the results are. It's not that difficult because you just go back to the expression for A and take the derivative. And here's the expression for A. It's got the 1 over delta in it. The delta term didn't have any of the values of y, so it can come outside. The derivative with respect to y of these quantities here, well, you can see right away the first term has the y values in it. So for each of those terms in the sum, when you take that derivative, you're going to get 1 over sigma I squared, right? So that will come outside the sum. And then what's left is the sigma of xi squared over sigma I squared, because that doesn't have any dependence on the quantity we're differentiating with respect to. And something very similar happens for this second term. The xi over sigma I squared, that doesn't have, when we differentiate with respect to y, there's nothing that comes in from that. And so the only thing when we do the derivative that we're getting a derivative from is this last summation here. And so the result that we get for dA dyj is given here. dB dyj is something very similar. That's equation 620, and now we put those back in order to calculate our error, in this case the variance, in A. So this expression here, that expression there, give us the errors that we need, or the variances, and then of course we take the square root to get the standard deviations. So we're almost finished. You can see from these kinds of expressions that when we do the evaluations of sigma A and sigma B, when we do the evaluation of A and B, we have all kinds of sums like the two that are given here. The sum over all the data points of 1 over sigma I squared, the sum over all the data points of xi squared over sigma I squared, and so on and so forth. So in order to do that, which is what I'm asking you to do for one of your homework problems, once you're given the values xi, yi, and sigma I, you'll form columns of all the values that are needed in evaluating those sums. Then each of the columns will have these products or quotients, and then you'll sum up the columns because each element, each row within that column represents one particular data point and the values of these quantities for each of those data points. So you sum those columns up. Those will give you the summations that you need, and then we substitute those into the equations to get the values of A and B, and of course sigma A and sigma B. When you're done, you quote the results. Here might be results that would be appropriate for some kind of a calibration measurement that you might do in the nuclear physics laboratory. And of course, we just follow the standard procedures. When we quote final values, we always have 2 significant digits in the error, and then we round off the value itself so it ends in the same decimal place that the error does. Okay, so final step is to determine how well the agreement is. So if we look at our chi-square values for each of our individual data points, and then we sum all of those up, okay, we did that before, but let's ask ourselves, once we've done this sort of thing, now find the reduced chi-square value, like we talked about back in chapter 4. So you sum up the chi-squares of all the data points, divide by the number of degrees of freedom. In this case, n is the total number of data points, and sub c is the number of constraints. In the case of a linear function, there are just 2 constraints because we've determined the a and the b values from our data set, and so that has removed 2 of the degrees of freedom from our original n degrees of freedom since we had n data points. So the number of degrees of freedom is now n minus 2. And we ask ourselves again, what do we expect to get for that chi-square, that reduced chi-square value? If chi-square on average, if the deviations in our numerator, the expression for chi-squared, were roughly 1 standard deviation, then the sum of that ratio in the chi-squared expression would be approximately n. Not quite n, because it would actually have subtracted from it the number of constraints. So the expected value for chi-squared would be approximately n minus n sub c. And if we divide chi-square by nu, we would expect to get 1. Again, when we say we expect to get 1, that would be if the scatter of the data points around the fitting line, in this case a straight line, is about the same as the uncertainties in each of the data points. That's what happens when you get a chi-square equal to 1, and you would say, wow, that makes sense. Our data are scattered around the best fit line just about the amount that you would expect based on their uncertainties. So that would be a linear fit where the error bars pretty much for all the data points reach the line. And there's one more thing to add to what was talked about in Chapter 4 that we can do in order to test to see if our value of chi-square that we got is a reasonable one. The rule of thumb, of course, is reduced chi-square should be about 1. But how close to 1 does it have to be? And there is a probability function for the chi-square distribution that's given by this. It means if you have a function that has a certain number of degrees of freedom, then the probability of getting a particular value for chi-square when you take a set of data points out of the parent population is given by this complicated looking function that comes from Chapter 11. Right? That's the probability of getting a particular value of chi-square. But what's usually more helpful is the integral probability, which is the probability when we integrate the chi-square distribution from chi-square to infinity. It's the probability of getting a value of chi-square or larger from a randomly collected sample of the parent population that has a certain number of data points in it and thus a certain number of degrees of freedom. So, again, this is from Chapter 11. What would we expect that integral probability to be? So if the reduced chi-square value were about equal to 1, what would that probability be? Well, it's not too difficult to think about that. And in the limit of having a very, very large data set, you can look in the back of the book. There's both a plot that shows this integral probability function, and there's a table, and it shows that in the limiting case of a large number of data points, the probability of getting a chi-square value, a reduced chi-square of 1, is just about exactly 1/2, which would mean half the time you'd get a reduced chi-square value greater than 1, half the time you get a reduced chi-square value of less than 1. So if you get a particular reduced chi-square value, maybe you get 1.3. So how do you know whether that makes sense? You can go to the table and find the probability of getting a chi-square value of 1.3 or greater. And if that probability is really, really small, then you know there's probably something amiss. If that probability is something on the order of 0.5, 0.2, 0.3, something like that, then the chi-square value that you got from your data set happens fairly frequently. If, on the other hand, the probability is way too high, then that might mean something is also amiss. And so, again, what this all comes back to is when we have a particular data set and we perform, in this case, a fit to a straight line, what do we conclude if the reduced chi-square is about equal to 1? And then the limiting cases where that value might be much greater than 1 or much less than 1. And these two, we would see something's wrong by in a more formal way by evaluating the probabilities of getting a chi-square value that large or larger. And if that probability is either too large or too small, if it's very, very far away from 1/2, then we would conclude that our data really don't fit that line very well, and we might want to go back and re-examine the measurements that we made or perhaps the uncertainties that we're assuming. All right, so that's a very quick overview of Chapter 6. Reading the text will fill in more of the blanks, and I'll see you in class.